Dr. Hassan here again. So in this lecture, I want to show you how to solve a kinematic problem for relative velocity using center for zero velocity. What do we mean with center with zero velocity? If a rigid body, any rigid body rotates, we know that that rigid body would have a center for rotation at that minute. Like if you look into a potato like this, if one side of it moves like in this location, like assuming this is B, and then A moving like this, we know that at this instant there is a center for this rotation, and that called center for zero velocity. If we know where the center is, then we can treat it like rotation about fixed point and make it so much easier. Now, how can we find the center for zero velocity, where that center is, or how to locate it? Now, let's look into different cases. Now, in this case that I have two velocities in different directions. Now, what you could do, we know that the center is somewhere on the line which is perpendicular to velocity. If the direction of velocity at B is look like this, I can actually find the R. The R would be something look like this, right, for B. Now, how the R would look like for A? Click on the A and then go so this is actually the radius for the B. Now, and then this is going to be 90 degrees. Now, do the same thing for A. Now, if you do the same thing for A, you would find the center. And this is where the center is. I'm going to call this point O. Point O, or we call it center for zero velocity. Now, or I can call it like OC, whatever you like to call it. Now, in this rotation, which is going to be center for zero velocity, I'm going to call this one OB and this one OA. Or you can say this is RB and this one is RA. Let's look into different cases. Now, the first case that I solved you was where the velocities they do not actually parallel together. We have two different velocities. Now, if I solve like a slightly different example, I would say, like in the problem that we solved last time, the direction of velocity of B was look like this. And then here was 30 degrees. And then we had another point, velocity of point C was in this direction. Now, in this case, velocity of point B was 6 meters per second. And we wanted to find how much velocity at C is. Now, in order to do that, you can say you could go perpendicular to each of those velocities. So I'm going to go perpendicular to the first velocity and perpendicular to the other velocity. So let me just change the color so you can visibly see it. Now, the center would be somewhere on this line for C, right? Because velocity is in this direction. And for B is going to be somewhere in this direction. And then if you continue, you get ended up at the point O, where the intersection of these two velocities. Now, how we do that? You consider the velocities, you add the velocities at their point of action, you draw a line parallel to that, and then same thing parallel to the other velocity. This one I'm going to call it RC, and then the other one I'm going to call it R. This was point B, so I'm going to call this one RB. Now, how this thing make our calculation easy? By the fact that we can say velocity at B is equal to RB. Omega is the same for both these points. And then that omega is actually omega of BC in this case. Now I can say velocity of B is equal to RB omega BC. At the same time, velocity of point C is equal to RC omega BC. Now, the thing that I don't have, in the last problem, this distance was 0.6 meter. The thing that I don't have, I don't know how much RB is and I don't know how much RC is. The method that we use, we call it law of sine. I don't know whether you remember law of sine or not, but law of sine was something look like this. Sine of A over A is equal to, this one used to be the small a is equal to sine of B over B is equal to sine of C over C. And then this is actually, if you have a triangle look like this, and the angle here is A, B, C. The side opposite to A, we call this small a, the side opposite to B, small b, and the side opposite to C, small c. And this was law of sine. So I'm going to use law of sine to actually find RB and RC. So the angle here is 60 degrees, the angle here is 90 degrees, the angle here is 30 degrees. Now in this triangle, I know that RB, so let's do the law of sine. I'm going to say RB over sine of 90 degrees is equal to RC over sine of 60 degrees is equal to 0.6, which is actually this distance for that, and that's actually over sine of 30 degrees. Then the last one is uh, 0.6 divided by sine of 30 degrees. Now if you cross multiply this, you would be able to find RB and RC. Now if I cross multiply the first one with the last one, I'm going to get RB is equal to 0.6 into sine of 90 degrees, which is 1. It would be 0.6 times, which would be just simply 0.6. Now we got 0.6 divided by sine 30, divided by sine 30, and then 0.6 divided by sine 30, which is 1.2. Similarly, you can find RC. So RC from this problem, RC is equal to sine 60 times RB divided by, or like the other way, I can go this way. I can say 0.6 times sine 60 divided by sine 30. The answer is 0.72. Now when I know both RC and RB, let's go to this equation down here, right? In the first equation, velocity of B is 6, so I can say 6 is equal to RB, which is 1.2, omega BC, we don't know. And then we can solve for omega BC. From here, omega BC is equal to 6 divided by 1.2, and the answer is 0. Yeah, so I can actually solve for omega BC, and then if I know omega BC, then I can just put it down here to find VC. So I can say VC is equal to RC. RC was 0.72 times 6 over 1.2. And then you ended up at velocity of C equal to 1.44. Something baffled me for a second. 0.6 times 2. This will be half, sorry. This will be half of that, not. So will be 0.72 divided by 2, which is will be 0.36 meter per second. Then we can continue and solve more problem using this this method. So a portion of this method is I can say a portion of this method is when we have two velocities which are not actually parallel together. So assume a case where we have velocities, like in the first case that we have velocities where not parallel together. If I have velocities which are parallel together, a case like this, if you have 2 points, where in these 2 points one point is velocity look like this, the other point velocities look like this. Now, if the velocities are parallel together, we should know magnitude of each of them. Or we know like magnitude of this, but again, if you don't know the magnitude, we won't be able to identify where they are. But again, if you have magnitude, we can just simply draw it like this. And the center will be down here. So if this is velocity of A and the other one is velocity of B, and that will be the center of rotation. Now this is point O. The first one is going to be RA and the next one is going to be R of B. We can go with the same explanation that we have before. There could be different cases too where we have 2 velocities and then 2 velocities are actually parallel together. One of them is going to go like this, the other one is going to go like this. So this is velocity of A and the other one velocity of B. In such case, the point of intersection would be somewhere here. That's where we can see the point of intersection is the point O would be somewhere down here. Now, I want to go to continue the topic with more examples. So the next example that I want to solve is example from the text, which is going to be this one. Okay, in this example, we have 3 points, or we have 3 components. Now, those 3 points is point A, point B, and point C. We know velocity of A is 0. Velocity of B, we can somehow calculate it. Now, we want to find how much velocity of point C is in this example. Now, in order to find velocity of point C, I need to follow the same process that we explained before. So velocity of, just to go forward, I need to know what types of motion each of them they have. So AB, the types of rotation that we have at AB, this is actually rotation about fixed point. And now for BC, that's actually simply general motion. And for block C, which is a piston, for that we just have simply a translation. Now in this example, as you can see, as we rotate bar AB clockwise, then you would see that bar BC rotates counterclockwise, and then this will push the block up, and then in the location C it's going to go up. Before I start the problem, I'm going to start with just rotation about fixed point at point B. So let's draw bar AB. Bar AB is going to look like this. So this is A, this is B. Then at the location of B, the direction of velocity would be something look like this, perpendicular to bar AB. Now perpendicular to bar AB, the value of it would be R omega. And then, so I can say velocity at B is equal to R omega. And then the value for omega is 10. The value for R is 0.25. So 0.25 times 10. And the answer is 2.5 meter per second. So I found velocity of point B. Now at point C, I know that guy is going to go up. And I want to use the concept of center for zero velocity. Now let's look at bar BC. Bar BC, that's how it looked like. The angle here is 13 degrees, 13.6, so odd degree. And then I don't have much more information on this. Then velocity at location of B, I know that if I look into AB, which was look like this, the velocity of it was at this point was in this direction. That's velocity of B, which is equal to 2.5 meter per second. Velocity of C direction wise, we talk about that velocity of C is going to go all the way up. So now I need to find the center for zero velocity. To find the center for zero velocity, I'm going to go from each of those points, each of the points that we have. So we have VB and we have VC. I'm going to go perpendicular to VC. So perpendicular to VC is going to be like this. I'm going to go perpendicular to VB, which is going to be, it's going to be, I don't know why I keep selecting this thing. And then that's where the intersection of these two is. I'm going to call this one point O. That's the center for zero velocity. At this location, this bar at this moment rotates about that point. Again, that point is away from your body, we don't care, but that's actually the point of rotation for this bar at this minute, at this instant. The angle here is 45 degrees. I need to find RC and I need to find RB in order to find the rest of my calculation. RB is going to be like, I need to find the angles too, right? So if you remember, if you look into this, RB is actually along AB, right? And then this was the angle here was 45 degrees. Here is 45 degrees. That will make the angle in the other side 45 degrees as well. Sorry. So if I continue like this, just I have to be a little bit more accurate. This is how our triangle look like. So if this is 45 degrees, down here is going to be 45 degrees as well. Now I need to find two more angles. Now the first angle here is 13.6. The sum of these two angles will be 90. So 13.6 minus 90, and that's 76.4. So I have 76.4. And then again, the summation of the angles in a triangle will be 180. So you have 45, 76.4. The angle here is going to be 58.6. The length of this bar is 0.7 feet. 0.75 feet. Let's use law of sine. Let me just to clean up a little bit some of this stuff that I draw them unnecessarily. So one side is RB, one side is RC, one side is 0.75 feet. So I need to write law of sine. So law of sine will be sine of 45 degrees over 0.75 feet is equal to RB, which is actually across from sine of 76.4 divided by RB. And this is equal to sine of 58.6 divided by RC. Then I would be able to calculate for both. Yeah, I would be able to calculate both. Just bring this slightly down. I would be able to calculate both of those. Now, if you cross multiply this relationship, you would find RB. Okay. Find RB is equal to RB is equal to 0.75 sine of 76.4 divided by sine of 45 degrees, and the answer for this is equal to 1.03, and then RC is equal to 0.75 sine of 58.6 divided by sine of 45 degrees, and the answer for this is actually equal to 0.91 meter. So now I know RB, I know RC, and then we already know the velocity of point B that we calculated last time, and then that velocity was, just scroll up a little bit, yeah, that velocity was 2.5 feet per second. Now, because I know that velocity, I can say, I already know that VB, actually I have it here, the unit is feet per second. It is feet per second, not meter per second. Now I have velocity of B is equal to, the bar that we are talking about is bar BC. So velocity of B is equal to RB times omega BC. Same thing here. Velocity of C is equal to RC omega BC. Now velocity of B is 2.5 is equal to 1.03 omega BC. From here, omega BC is equal to 2.24 radian per second. Now I'm going to get it from here and plug it into down here. So I'm going to say is equal to RC was 0.91 times omega BC, which is 2.24, and the answer for this would be 2.2 meter per, sorry, not meter, feet per second. We actually solved this problem without using anything from vector, without using any I, J, or something similar. So I want to expand the lecture and use one more and then solve one more problem. In the next problem that I want to solve is it's very similar to the problem that we solve. It looks like the guy in YouTube looking to fix a fridge. So there you go. In this problem, the question asks me to find velocity of point O. So I want to find velocity of point O. How much is the velocity of the center? So let's talk about what types of motion you can see in this problem. So the question asks me find velocity of, do we have the touch? Yes, we have. So velocity of point O is equal to how much? In order to find velocity of point O, we have to start from point A, going to point B, going to point C, then going to point O. What types of motion we have for each of them? So for AB, the types of motion is rotation, And then for BC is going to be a general motion. We already know that. And then the funny part is that the wheel that you can see there, that's what we talked before, is a general motion, but actually the center for rotation, we need to find it where the center of rotation for that is. Now I'm going to start from bar AB. In bar AB, point A, point B here, and then the angle here is 60 degrees. The length of the bar is 0.4 meter. Now the velocity of B is going to be perpendicular to this cross section, so it's going to be something look like this, and velocity of B would be equal to R omega, and the radius is 0.4. Omega is given as 6. This is ended up at 2.4. This time I'm not going to make mistake. Meter per second, because the unit is meter. Velocity of point C. I don't know what the direction for velocity of point C is. Now I'm going to go all the way to the wheel. If you go to the wheel, so I'm going to draw the diagram for the wheel of the gear, and then draw the diagram for BC. So the diagram for BC, and then the diagram for the gear. For BC, the velocity of B is actually in this direction. That's 60 degrees. The angle here is going to be the angle all the way with the x-axis. It's going to be 30 degrees. How I found it? I just cheated from the other problem. Yeah, we just solved very similar problem a minute ago, and then I used the value for there from 30 degrees. Now the velocity of B is actually look like this. Sorry. Okay, velocity of B, the value is 2.4. The angle here is 30 degrees. I don't know what's going on about point C. So point C is the top of the gear, is down here. And point O is here. There's the point down here, right? And then that point actually is, again, when we talk in the previous chapter, we said that at this instant, if you have a roller that rolls, if you have a gear, if you have a wheel, at this location, your velocity is 0. So I'm going to end it up something look like this. So I know the center O is going to go with this direction at that minute. The C is going to go in this direction. So if you connect these two together, you actually ended up with the center here. That's how it's going to look like. But what I'm going to get from this picture, I'm going to get into that velocity of C is going to be in this direction. That's where the direction of velocity of C is. Now I want to find the center. I want to find the center for zero velocity. To find the center for zero velocity, we go with the same concept. We draw the radius for each of them and then find the intersection of those radius. So the radius for C is going to be in this direction. The radius for B is going to be in this direction. This is so similar to what we solved a minute ago. And then the length for the gear, that length actually is 0.6. Yeah, it's very funny. I guess I'm just solving the same problem that I just solved it up there. So down here I have 0.6. To find the angle for this one is going to be 60. The angle here is 30. The angle here is going to be 90 degrees. I'm going to call this one point O, or point of rotation, whatever you want to call it. In some textbook they call it IC. In some other textbook I'm going to just call it simply a point O. Because we have point O, I'm going to call that O prime. So this is going to be RB, the radius for point B, and that's going to be radius for point C. So we could continue with the same thing that we did before. So velocity of B is equal to RB omega BC, and the next one, velocity of C, is equal to RC omega BC. From the first equation, again, we already calculated this, our length of RB on the top, that's ended up as 1.2, length of RC ended up as 0.72, and then we can say velocity at B is equal to 1.2, so I have on one side I have 2.4 is equal to RB, which is 1.2 times omega BC. You ended up omega BC is equal to 2.4 divided by 1.2, and the answer for this will be 0.0, just is going to be 2. Now if the answer here is 2, then you can calculate velocity of C. Velocity of C would be equal to R of C, which is 0.72 times 2. The answer for this thing is going to be 1.44. I'm going to go down here, so I have velocity of C is equal to 1.44. Velocity of O, so look at the distance. Here is 0.1, here is 0. If you use similarity between triangles, you would end up finding velocity of O is equal to 1.44 divided by 2, which is 0.72. Okay, thank you very much for watching this video for how to identify the center for zero velocity, and use that to, if you, by knowing velocity of one point, you will be ended up finding velocity of the other point. Now the next lecture that we have in a minute, that's going to be about relative acceleration. So by then, see you in a minute. Bye bye.